Good. All right. I'll try to catch up a little time here. I know we're about to talk behind. I'm going to talk about one particular instrument on the LCROSS mission that really wasn't published on in any of the science papers, and we're trying to write this up now. And it's the twin of the nadir viewing near-infrared spectrometer. LCROSS had two spectrometers, one looking straight down and one looking off to the side towards the sun. They had identical wavelength ranges and resolutions, are basically copies of the same instrument. And the solar viewer had a diffuser on it that allowed it to look at the sun. And that diffuser had a very wide angle because we didn't exactly know when LCROSS was launching because we were tied to the LRO launch date, which we couldn't adjust or change in any way. So we had to adapt to wherever the sun might be at our particular impact time. Turns out for our impact date, the sun was in a very good position to do this experiment. Basically, what this diffuser allowed us to do was look at the sun and get very high signal-to-noise on the spectrometer. I've got a little graphic there to the right showing the radiance as a function of wavelength. The blue dots are the data, just showing the radiance for a single scan. Each scan was about 0.6 of a second. And the red curve shows the signal-to-noise with the right axis showing we had certainly for most parts of the spectrum very high signal-to-noise, sometimes over 1,000, which is great if you're trying to measure very small things. So the intent of this experiment was to look for any occultation of sunlight by debris or plume if it by chance was still there 4 minutes after impact. So it was a kind of experiment of opportunity. This just shows the two spectrometer entrance apertures. There's the nadir viewing telescope here, and this little optic right here is just a diffuser, very simple design, feeding into a fiber that looked off to the side towards the sun. So again, as I mentioned, we were trying to, we were thinking perhaps there may be some material as we descended through the plume. If it got high enough and we survived long enough and had sun on that solar viewer, that we might be able to detect the plume. This shows a visible convex image for the plume and Cabeus. This is at about 20 seconds after impact. The plume was about 10 kilometers across. And this builds off of, well, off what Dana described. LCROSS was a hollow impactor. That Centaur was basically a large oxygen and even larger hydrogen fuel tank. So two hollow impactors, if you will. And Pete Schultz and Braden Herman at NASA Ames Vertical Gun did experiments and showed that these hollow impactors create this vertical plume here, as opposed to a more solid impactor, creates much more of a lower angle plume. This high angle plume is in addition to a low angle plume, and this actually probably was really important in the results that I'm going to describe here. It got material to a very high elevation. So really, to set up the stage here, LCROSS really created two plumes, a high angle and a low angle plume. And the figure here on the right shows integrated radiance from the ultraviolet visible spectrometer at LCROSS, which is looking down. Here's the impact. Here's the peak in brightness. And this is really consistent. We've been able to model this with two plumes, a high angle and a low angle plume. This part is the low angle, and if it was just a low angle, it would have dropped away well after 75, 100 seconds. However, we see this constant flux here. That's in part because we have a plume that's filling our aperture. So essentially, we have constant flux into the instrument as we descend. And then finally, we get so low that we start to lose parts of the cloud in the field of view. And finally, we're descending actually through the cloud in this final part of the spectrum. So here's the high angle plume, low angle and high angle, and this is just the low angle plume itself. This high angle plume did get quite high. It was observed from the ground by Apache Point. A variety of papers, or at least one or two papers, are in work on that, I know, and the results are very intriguing. To actually have particles out here falling down and us to see them, they would have had to reach probably about 12 kilometers or so to still be descending. Oops. And Pete Schultz points out in his science paper that there are some interesting ghosts in the near-infrared image images as we're in our final descent and imaging within the dark crater that are possibly due to dust as well. So there's other evidence that there should be a plume late following impact. So the NSP2, that's this solar viewing spectrometer. It's got the wonderful acronym NSP2. Was observing towards the sun, as I mentioned, the shepherding spacecraft where it was on, came down about 3 kilometers from the Centaur impact site. So these are, this is a picture by Will Marshall showing the exact location of the Centaur impact and shepherding impact sites inside Cabeus. This little circle circles the Centaur crater right here. This is in a radar image, actually, from Goldstone. And the shepherding impact site right there. And this shows it in our near-infrared camera, the Centaur impact site. So we came down kind of parallel to the sun, which is up here to the upper left, kind of at the 11 o'clock position. Our NSP field of view, like I said, was broad, so it can encompass many, regardless of where the sun might be. Turned out it was only about 12 degrees off normal, which is good for us, really high signal and an easy correction to make. And so we didn't come down directly behind, over here. That was a part of the impact site selection process. So that gives the general geometry for these observations I'm describing. What I'm showing here are the final 20 seconds or so of scans from this instrument as we descended into the crater with the shepherding spacecraft. Remember, the shepherding spacecraft's descending at the same speed as the Centaur impactor, which was about 2.5 kilometers per second. So it's hightailing it to the surface of the moon as well. What I show here is the average of 5 scans, well, in time, not in time, across 11 pixels. So basically, I did a moving average to build as much signal-to-noise in these as possible. And then I ratioed consecutive 5-scan chunks to a reference scan made about 30 to 40 seconds prior to the impact. So it basically said, hey, we're above the cloud. This is just a clean reference with no dust, no water vapor or anything in it. And that's basically this black dash scan that you see here. And you see it's relatively flat, which is good. You want a reference to be relatively flat. That's a good thing. What you see then descending down here are scans taken subsequently, ratioed to that reference. And I have the approximate altitudes above the surface, which that 5-scan average corresponds to. So this reference was about 46 kilometers, this was 41, 36, and so on. And what you can see is we start to lose signal, this drop overall in signal. You start to see a change in continuum, and also you can see absorptions coming in across various wavelength bands here. So we certainly seem to be seeing something, and it kind of makes sense in terms of you really start to see the signal right about 28 kilometers above the surface and really peaking, starting to peak around 16 kilometers above the surface, which is still quite high above the surface. So this shows a linear fit to this spectrum here, the 6-kilometer spectrum, where we have the strongest signatures. There's just a linear fit where we predominantly added water and water vapor, makes up most of the fit. It's much better than 3 sigma fit for water vapor and water ice to this spectrum using a chi-square over nu statistical method. But we also see some other interesting things, including potentially hydrogen fluoride, which at first I was scratching my head, but then talking to ISRU folks, they say, hey, you mix water and lunar dirt and you heat it up, you're going to get hydrogen fluoride. That's something they see in all their experiments. And maybe some other hydrocarbons out here that could be still burning Centaur, I don't know, or something else that is actually real to the moon. To model this further and to really understand better how much of water and water ice was there, because that's predominantly what I was interested in, I built a Monte Carlo model where I basically generated a hemispherical dust cloud and ran millions of photons through it with the various mixes of dust, water ice, and water vapor. So it's a pretty simple model, but it's most appropriate for doing these kinds of transmission calculations. And I did a variety of fits against changes in the total water gas column, total ice grain radius, etc. And this shows some of those results. This shows the relative brightness as a function of wavelength. The data, the circles with the error bars shown, and the models are the various lime colors shown here. This is for total water and water molecules per cubic centimeter. And you can see a best fit, the black line gives about 2 times 10 to the 16th per cc, which is about what we saw from the NADAR spectrometer at the later times as well. That's equivalent to about 10 or so kilograms of water total in the plume, given the geometry I assumed for this plume here. This shows the best fit against ice grain radius, because I was wondering, hey, can we actually say anything about the size of the ice grains? And maybe. It certainly seems like it's not 1 micron or less, but it's hard to say if it's 4 microns or larger, given this kind of data. What I would conclude is that the ice grains aren't particularly small. They're not submicron. They're probably larger than a micron. There's other evidence I'll mention here in a second for that. Yeah.
You have 1 minute and 30 to the question time, and then 2 minutes after that to the next speaker.
Perfect. Summary right here. Thank you, Dana. So NSP, I think, are some of the best observations of dust and water, both ice and gas, that actually LCROSS made. The spectra are less complicated than the NADAR viewing spectra and easier to actually work with and fit. The linear Monte Carlo fits identify the water and the vapor very well, high statistical certainty, and actually constrain the total water and total ice quite well as well. For these water ice grains to be persistent, meaning to have gone up and come back down 4 minutes later and have been in sunlight that entire time, they have to be relatively pure. It's pretty hard to actually pin a number on that, but it's something probably better than 50 or 60% based on what similar analysis you do for comet particles. And so the last point I'd like to make is this higher angle plume is probably consisting of material closer to the surface in the top meter or two. It's part of the dynamics of the impact. The higher velocity material in that plume, that high angle plume, would have been excavated very near the surface compared to the low angle plume. So this is maybe one more bit of information we can say about at least this one spot on the distribution of water ice within the topmost meter of regolith. And that's it. Yep, thank you.
Thank you.
Well, thank you, Tony. And do we have any questions typed in here? I'm not seeing any yet. Okay, do we have any hands raised? Any questions in the audience for Tony? Don't see too many people here. All right, well, Tony, I think everybody's just trying to help us get back on time, and I appreciate your talk very much. Maybe some more questions will come up in a bit.
And during the session, you could always ask your questions through the chat, and Tony, you could answer them in the chat window as we move along.
Okay, great idea.